So we're going to go into neighborhood method now. But before we can do that, we first need to go through what's called a baseline predictor. And before we can go to a baseline predictor, we first want to talk about the general notion of a parameterized model. Now we're going to see also parameterized model in a very different context in the next chapter with Bayesian analysis. In general, we want to build a model that is some mathematical representation of the problem we want to solve. Sometimes this model carries with it a bunch of parameters. We'll see a lot of parameters today. And these parameterized models will go into the so-called training phase first, where you have some observations, but you also have the ground truth. And you take the observations, make prediction, and compare with the ground truth. Then the difference is what something that you want to minimize by tuning the model parameters. After this step of training, you have optimized model parameters. Then you go into the actual real action, which is the prediction step, where you take these optimized parameters in the model, optimized by the training phase with the known ground truth, and then you take the observation to make predictions. Sometimes other people have the ground truth, like Netflix had the ground truth for the Netflix prize, but you don't. So training followed by prediction. In training phase, we train your parameter, just like a voice recognition system on your computer or phone or car, and you first train them by speaking out certain known sentences. These sentences are the ground truth, and then the computer will take in the observation, which is the recording of your voice, and then train the parameters before going into the actual action of making predictions in the future for you. All right, so having said that, let's go into the baseline predictor. This is the step number 1 before we can afford to go to step number 2 on neighborhood predictor. So baseline predictor does not utilize the global structures of the users and movies rating. We're going to start the baseline with the baseline of the baseline. That's the laziest predictor you can think of, the average predictor. Let's call that R bar. R bar is simply the summation of all the RUIs across all the UI pairs where there is a rating, and then divided by the total number of such ratings. That's it. It's simply the average. It turns out that in the Netflix prize training data, 100 million data points, R hat is 3.6. That is, over all these 100 million ratings, the average is 3.6. And we can say, well, that is our prediction. We predict that all the users and movies interaction will be 3.6 stars in the future. Clearly, this is very lazy. We can do a lot better than this. For example, we know that certain movies are better and certain reviewers are harsher. So let's say the predictor, R hat, is R bar, but with some bias terms. So B, bias terms with regard to the user, and bias term with regard to the movie. So our R hat UI is the average predictor, the laziest one, plus some bias term on that user, and some bias term on that movie. And now we can look at the root mean squared error. We can also take the square root of this root. So we'll just look at the mean square error, because that doesn't change our answer of the optimal parameters. So we look at the summation of the difference squared, difference between RUI and R hat UI squared. We can also delete the step of dividing by the total number of ratings, because that's just a constant that doesn't change our answers. So this is our objective function for the minimization. Minimize over the set of BUs and BIs the summation of the square of the differences between the ground truth RUI, which you have in the training phase, and the prediction R hat UI, where R hat UI assumes this formula. Okay, so this is the function involving some squares of the BU and BI terms. R hat is not your variable because it is just the average, say 3.6 for Netflix, and the BU, BI are your variables. That's an optimization problem. You've got an objective function, which is a square, therefore not a linear programming anymore, but we'll see this is a nice nonlinear programming. And there's no constraints. Okay? The variables are the BU, BIs, and the given constants are the known truth RUIs, and this simple scalar R bar. That describes the baseline predictor training optimization. So let's take a look at a particular example of this. Maybe get rid of the R because we are effectively taking the square root of the error, the mean square error minimization, or the total squared error, since we're not dividing by the number of ratings either. Let's say we have just 2 movies, A, B, and we just have one user, 1. So this is a ridiculously small example. In fact, it's so small that we have more parameters than we have data points. We have 3 parameters, BA and BB for the bias terms of the 2 movies, and the B1, which is bias term of this single user here. We have 3 parameters, and we have 2 known ratings from the ground truth, R1A and R1B. And what is our minimization problem? It is looking at the square of the difference between the prediction and the ground truth. Since we're taking the square, it doesn't matter which way we write out the difference. Let's say we write out R hat minus R. That is B1 plus BA plus R bar. Okay, this is our prediction. R hat of 1A minus the actual 1A. This thing squared plus the other error, which is 1A, B1 plus BB plus the average R bar minus the actual 1B rating squared. So this is the R1B hat minus R1B. This is the R1A hat minus the actual R1A. Okay, we take the sum of the squares of the differences, and that is the objective function. We want to minimize this objective function subject to no constraints over the 3 optimization variables, namely our 3 model parameters, BA, BB, B1. So our question is this an easy optimization or not? It's clearly not linear, but it is an unconstrained quadratic minimization over the variables. It turns out it is a very easy problem. It is so-called least squares problem. Okay, well, minimizing so-called convex, we'll come back to this in a minute, convex quadratic function over no constraints. And this is a very nice nonlinear optimization. In general, we say a least square problem is the minimization of the following vectors L2 norm. First of all, what is L2 norm? So given a vector x, want to measure its size, one standard way is L2 norm is the square root of the individual entries squared, summing over all the entries. We often don't like the square root thing. We take the square of the L2 norm. So square of the L2 norm is simply the sum of the xi squared over I. It's a very standard way to measure the length of a vector. And we would like to, in the square, minimize the L2 norm square the length of the vector AB minus C, where B is our variable. A is a known matrix, C is a known vector. Say if A is n by m, then B is m by 1, a column vector, and C is n by m by 1, another column vector. In the particular case we just saw, we can also write this problem, minimizing this expression in this standard form. It looks a little weird, but you soon see it's all right. The matrix is 1, 1, 0, 1, 0, 1. The variable vector we have is B1, BA, BB, and the constant vector term we have is R1A minus R bar on R1B minus R bar. This is our A, this is our B vector, this is our C vector, just to conform to the standard expression that we want to minimize in the least squares problem. You can easily check minimizing this is this L2 norm squared is the same as minimizing this expression. Okay, for example, this is just saying B1 plus BA minus R1A plus R bar, and that's exactly this term, right? And then you can write out the other term, and then just by definition of the square of the L2 norm, you see we're recovering exactly the same objective function. So we are in the baseline predictor problem solving a least square problem. So the question is, how do we solve a least square problem in general? Okay. Well, in general, we want to say we want to minimize AB minus C's L2 norm squared, which can also be written out as AB minus C transpose times AB minus C. Just it multiplying itself, inner producting with itself. You can write this out if you're not comfortable with the matrix notation in scalar format. You can write out a little 2 by 2 matrix A, 1, 2, 3, 4, and a little vector B1, B2 minus a little vector C1, C2. And then you can see that the derivation coming up is no mystery. But to save time, let's use the shorthand matrix notation. It's almost similar to our scalar operation. Okay. This will be AB transpose times AB minus AB transpose C minus another AB transpose C and plus C transpose C. And this can in turn be written simply as by transpose rule B transpose AB minus 2 times B transpose C plus C transpose C. Okay. Now we say if we want to minimize this expression over the variable which is B for a given A matrix and C vector, you can just take derivative of this with respect to B. Okay. Just like taking derivative with respect to, say, x of a quadratic scalar function, let's say, x squared plus 2x minus 3. We take the derivative, we get 2x plus 2. Right. Here we can take derivative with respect to B, and we get the following. 2, because there are two B's here, times A transpose A times B, minus 2, because of this 2, take derivative with respect to B, we get A transpose C. All right, now we set it to be 0, set this to be 0. Now, why is setting the derivative to be 0 going to give us the right answer? We'll come back to that in a minute. It sounds intuitive, but we will soon see that there's some convexity argument behind that. But right now, they just say set it to 0. And that means A transpose A times B equals A transpose C. This is the solution to our least square problem. If you want to solve this problem by picking the right B, well, the right B is the answer to this equation. What kind of equation is it for B? It is a linear equation. A transpose A is just another matrix times B equals another vector, which is A transpose C. So as long as we can solve this linear system of equation, we get the right answer, B star, that solves the least square problem. This is a general theme that minimizing a convex quadratic function boils down to solving linear equation, because you take derivative once, you get quadratic back down to linear equation. So everything that we're talking about eventually now boils down to a simple least square solution. So let's take a look at this one more time. We say our baseline predictor is the lazy R bar plus bias term for the users and the movies. Then you look at the difference between the actual R and this R hat in the root mean square error sense, which means you're looking at the square of the L2 norm, and you're minimizing over BU/BI that function. It turns out picking the right BU/BI and therefore completing this baseline model boils down to solving this kind of problem. And this kind of problem is called least square in this format. And the least square solution is simply the solution to this linear equation. We'll go through a complete numerical example towards the end of the lecture, but this is a quick summary of where we have been. Okay. Now you may wonder, this is kind of complicated. Why don't I just pick BU/BI to be the average rating of across all movies for this user and average rating across all users for this movie? Well, it turns out that's a reasonable guess, but it does not necessarily minimize our error metric, which is root mean square error. So all we're doing is to say, if you believe in this model, stick it into our error term, then you got to solve a least squares problem, which can be efficiently solved by solving linear equation, just like Google PageRank solving linear equation, but over there it's a very different set of equations. And then once you get the optimal BU star BI star, stick it back in here, you get your predictor that minimizes RMSE. It turns out that that's almost a good idea, except you need something else. You often encounter what's called overfitting. This is in the textbook and the advanced material, but basically it says that you can add so much parameters, all these BUs and BIs, and you can fine-tune them so well based on the ground truth in the training data that it loses flexibility and predictive power of the actual prediction. So we want to somehow minimize the impact of the parameters. We don't want to rely too much on hindsight perfection. We want to leave some room for foresight, because it's ultimately foresight that matters in predicting or recommending. One way to contain the weight of the parameter is to actually minimize the size, say L2 norm, of these BUs formed as a vector and these BIs formed as a vector. That's called the regularized least squares. If we use quadratic norm, then L2 norm is still a least squares. It's just a bigger least squares problem. But it does try to contain too much reliance on too refined parameters based on hindsight. Right. So after the baseline predictor, what we have is the following. We got the actual RUI. We got the baseline predictor R hat UI, which is the same as RUI minus R bar, the lazy average, plus the optimized BU and optimized BI based on solving the least squares. And we call this difference a shifted R, called R2D UI, just a shorthand notation. In other words, we have removed in this R hat R2D UI the impact of the average and the impact of the per user bias and per movie bias. And we're going to take this as the starting point into our neighborhood predictor to look at similarities across movies and across users. But before we do that, just a very quick detour for 5 minutes on the notion of convex optimization. Now, we have seen linear programming, which is a special case of convex optimization, where you minimize linear objective function over linear constraints, linear equations, and inequalities. So pictorially, that means you use linear inequalities to cut out the space of the variables into something called a polytope with sharp corners. And then you slide a bar, which is a straight line because it's a linear function, representing your objective function across this constraint set. So imagine an airplane flying above this constraint set. Okay, and then we want to identify the minimal value of this objective function over this kind of constraint set. It turns out what's really important is that you want your objective function to be convex, like a convex quadratic function, such as x squared, over the space of constraint set that is also convex, like an oval or circle. It's convexity that determines the watershed between easy and hard optimization problems. So what is convex optimization? It refers to minimizing a convex objective function, so we've got to define what is a convex function, subject to a convex constraint set. And to be computationally useful, this must be a convex constraint set that can be easily represented by some upper bound inequalities on convex functions. So we have to define what's a convex set and what's a convex function. We will encounter other forms of convex optimization in network economics, in internet pricing, in congestion control, in routing, and so many other topics. This is our first brief, quick introduction to this subject. And we'll see in this and future lectures that convex optimization is easy in both theory and in practice. But we just want to take 3 more minutes to introduce the basic notation before we bring them back just in time for the future applications in later lectures. So what's a convex set? What's a convex function? We can actually go into a whole course on nothing but convex analysis. And there are such courses in math department. But for today's purpose, we just need to specify with some pictures. A convex set is basically a set where you can pick any 2 elements in the set and draw a line segment in between. And the entire line segment also lies in the set. Then we call this a convex set. Say, well, that sounds like all sets are convex. Well, no. Some sets, for example, like this set, you can pick 2 points in the set, but part of their line segment, this part, does not lie inside the set. And this is a kidney-shaped thing that is a non-convex set. So generally speaking, we say a set is convex if we pick any 2 points A and B, then in this set, okay, C, pick C, then the entire line segment between A and B, which can be represented as theta A plus 1 minus theta times B, for some theta between 0 and 1. For example, when theta is half, then it is the midpoint between A and B, also lies in C. For all such theta, that's the key word, not for some theta, but for all theta. This is the representation mathematically of the line segment between point A and B. And by the way, let's say A, B are vectors in general in n-dimensional space. Okay. So pictorially, it just says that a convex set is a set where the whole line segment lies inside. It turns out the most important geometric property of a convex set is that any 2 convex sets that don't touch each other can be separated by a straight line, so that one set lies on one side and the other lies on the other side. And say, wouldn't this be true for non-convex set too? Well, not really. For example, one set is convex, the other set is non-convex. They don't touch each other, and yet you cannot separate them with a straight line. Of course, you can separate them one way or another because they don't touch, but you can separate them with a straight line. It turns out that this is the most useful property of convex set. But we don't have time to go through the implication of that in this lecture. Now, having specified what's a convex set, let's define what's a convex function. Convex function intuitively is a function that curves upward. Okay? And some function, for example, curves upward before it curves downward. Now, we know that if we look at a function f, its first derivative tells its monotonous, is it increasing, is it decreasing function? And the second derivative tells us whether it curves upward or downward. Let's say the function is single variable function, f of a scalar a variable x, let's say quadratic, because we're all talking about quadratic today, is x squared. Okay, you can add a few other, couple of other affine terms, say 2x minus plus 3. Okay. This, if you plot it, curves upwards. Or another function minus x squared plus 2x plus 3. If you plot it, it curves downward. Both are quadratic function. One is a convex, the other is not. In fact, the other, if you flip it, minus f of x for this function is convex. We call the function whose minus of that function is convex a concave function. So this is convex function. This is a concave function. Of course, it doesn't have to be quadratic, and it doesn't have to be univariate. It could be a multivariate function. But the idea is that if it curves upward, it's convex, downward, it's concave. Some functions are convex and then concave, like this sigmoidal function we'll encounter in social network influence models later. It starts out convex. At some point, so-called inflection point, it starts to bend downward. So this part, the second derivative is positive. And this part, second derivative, is negative. This curves up, this curves down, this part is convex, this part is concave. The whole function, therefore, is neither convex nor concave. Now, what kind of function is both convex and concave? We say, wow, that means you need the second derivative to be both non-negative and non-positive. The only possibility is that it is exactly 0. That means it has no curvature. That's the only way to make it both positive and negative. So no curvature means it is a straight line. It could be pointing up or pointing down, depending on the first derivative, but the second derivative is 0. In other words, linear or affine function is the only function that's both convex and concave. Now, these pictures are drawn on 2D, therefore they're talking about a single variable. But it's a multivariable function, then we have to talk about second derivative, slightly more involved. Recall your multivariable calculus course. Assume that you still remember or can quickly brush up your memory about that. If a function, let's say, of just say 2 variables, once you get hang of that, it's the same as many variables, is quadratic, s squared plus xy plus y squared. Okay, xy are single variable, but is a function of both variables. Now, what is a second derivative of a multivariable function? It's not a simple expression anymore. It's not a number. It's a matrix. With partial derivative of this function with respect to x squared and with respect to y twice, okay, and with respect to both x and y, with respect to both y and x. This is the matrix. You have to take partial derivative with respect to x and y, and in general, we say, given a function f of variables x1, x2, of xn, if we look at the partial derivative with respect to xi and then with respect to xj, this is the ijth entry of a matrix. That matrix is called the Hessian matrix, or in short, the Hessian of the function. So in this particular case, it is very simple. We take derivative twice with respect to x, we get 2. With respect to y, we get 2. With respect to x and then y, or y and then x, the same thing for us is 1. Okay, so this 2, 1, 1, 2 is the Hessian of this particular function, and this is the general definition right here. The ijth entry of the matrix is partial f, partial x, I, and then partial f, partial x, j. So how do we make sense out of saying that a matrix is positive? It's not that the entries of the matrix are positive, but it's about whether this matrix eigenvalues are all positive or non-negative. And you can check that this matrix eigenvalues are all non-negative, and therefore this function is a convex function. But in general, we say a function is convex if satisfy the second derivative test, where the Hessian matrix thus defined is so-called positive, semi-definite. And a matrix being positive, semi-definite means all the eigenvalues are positive or non-negative. Now you may wonder, what if my function does not have a second derivative? Its Hessian matrix doesn't exist. Some functions are not smooth enough that you can take derivative twice or even once. Well, it turns out that that's fine too. I can have a function with a sharp corner. Okay? At this point, we don't have a second derivative. But we can still define a function as convex or not, and this would be a convex function. However, since all our functions throughout the entire course are smooth enough that the Hessian matrix exists, we will just follow this definition. Okay. So, minimizing a convex function, which we know how to detect now, subject to a convex set, is a convex optimization, and least square is a special case because least square minimizes a convex quadratic function subject to no constraints. So finally, we're done with the baseline predictor, and now we can move on to the proper subject of today's lecture, defined neighborhoods